Swayam Prabha. Digital India. Educated India.
In this lecture, let us discuss about equilibrium chemically reacting gas mixture. In order to take the discussion forward, we would like to discuss about Gibbs free energy, which we have introduced in the previous lecture, and its connection with chemical equilibrium. That discussion needs to be taken ahead further, so that we are able to mature it to a point where we are able to develop an expression for equilibrium constant. We will see the application of equilibrium constant with an example problem, and then before we finish, we will discuss about heat of reaction. In the previous lecture, this is what we had derived towards the end. We had obtained an expression for the condition of chemical equilibrium in terms of the Gibbs function and stoichiometric mole number of species. These were the two important parameters in that summation. Then you recall that we looked at the definition of Gibbs function for species I, and we substituted that definition, the definition for SI that we had obtained earlier into the equation for GI, and therefore, we got an expression for GI like this. We try to take this forward further from this point. Now, we will assume that Pi is equal to 1 atmospheric pressure, and let the corresponding value of the Gibbs function obtained for that Pi value be represented by GI equal to Pi or rather GI with a superscript Pi equal to 1. Now, instead of writing 1 ATM, we just write Pi equal to 1, just for the sake of simplified nomenclature. Now, GI for Pi equal to 1 will therefore see some simplification, because on the right hand side, the expression that you originally had would now be simplified, because the numerator here is replaced by 1, and therefore, it becomes R log P ref. Ref of course, refers to a reference state. Now, if you combine the previous two equations, one is the GI equation, the other is GI evaluated at Pi equal to 1, you can get this equation connecting the two. So, there is a difference between the two in terms of RT log Pi. If you substitute the above equation into the equilibrium condition, because equilibrium condition needs the GI, therefore, it will turn out to be like this. And if you expand the terms on the right, what do you get? You get one term like this, the other like this, and remember that the log terms over here can be expressed in a form like this, where it is like natural log Pi raised to the power of nu I. Now, if you take a summation of these values, then they are expressed in terms of negative of the summation of the other term here, and we transfer the RT to the other side, therefore, that goes into the denominator. If you expand now, what you have on the left hand side, you have terms like this. If you go from one species to the other, say the first species natural log Pi raised to the power of gamma 1 plus natural log P 2 raised to the power of gamma 2 and so on. Finally, it can be expressed in this form, where it is natural log of product of the respective partial pressures raised to the stoichiometric mole number, and therefore, it is basically natural log of pi, which is basically representing that product form over I species. Therefore, the equation reduces to a form like this. Also, you must have noted that when we sum nu I times G I, that goes to 0, but when we sum nu I times G I at P I equal to 1, that is not equal to 0. Why is it so? Because you can easily see from the equation that we wrote earlier over here, you can show easily that that summation will turn out to be like this, which is not equal to 0, and that is what figures in the exponent over here. Now, we recall from the generic chemical equation that we had wrote earlier, where all the reactants were taken to the right hand side. So, we represented the chemical equation in this form: 0 equal to sum of nu I A I summed over I species, where nu I is negative for reactants and positive for products. Therefore, if you take a summation of this, which is Gibbs free energy of the products minus the Gibbs free energy of the reactants for the given chemical reaction, that is what you are going to get out of that, where the G I are evaluated at 1 atm pressure. So, this minus basically comes from the fact that the reactants are going to give negative contribution, because the nu I turns negative for the reactants once you transfer them to the right hand side. And the interpretation in terms of the Gibbs free energy is that it is Gibbs free energy of products minus Gibbs free energy of the reactants, which we look at, and therefore, you can sum it all through this equation that we have written over here, and that is what we are going to call as delta G evaluated at P equal to 1. So, that is the nomenclature we use over here. There is a further simplification, if you note over here, that we are using is that we are no longer going to call it as P I in this delta G expression, it is just going to be referred as P equal to 1, which inevitably means that for all the reactants and products individually, the P I was always 1 atm. Now, let us go back to the chemical reaction equation that we had looked at corresponding to the oxygen dissociation reaction, and if you recall that for 1 atmospheric pressure, this would start occurring from about 2000 or 2500 Kelvin onwards and get completed by around 4000 Kelvin or so. If you are to write down the delta G expression for this equation for P equal to 1, then how do you write it? It has to be written in terms of the reactants and products. So, effectively when this equation is written with everything transferred to the right hand side, you end up getting a half O2 plus a O. This of course is 0, and this is oxygen in atomic form. And therefore, the Gibbs free energy that you see is the difference between the two, the product minus the reactants, and with the stoichiometric mole numbers associated with them. So, you basically have a 1 over here, that gives you the delta G. Now, using all these concepts that we discussed about, we can write finally the pi Pi to the power of nu I expression on the left hand side will be equated to e to the power of minus delta capital G for P equal to 1 divided by R T, the product R T. For an equilibrium chemically reacting mixture, we know that G can be represented in terms of P and T. since P is already fixed at a value of 1 atm, therefore, when we talk about delta G for P equal to 1, then that basically becomes a function of temperature alone, because the pressure has been already fixed. Therefore, we can say that this term is purely a function of temperature, and that is what gives rise to the very important equilibrium constant, which we indicate as capital K suffix P indicated as a function of T. It is a very important idea to keep in mind that this exponential term is purely a function of T, and that is how the equilibrium constant also derives its functional form, that it has only dependence on T, because the pressure has already been fixed to 1 atm. Therefore, we finally write the equation in a highly compact form like this, where the product of partial pressures of all species raised to their stoichiometric mole numbers is equated to the equilibrium constant. How do we obtain the Kp as a function of T? It can be either obtained from experiments, not for all, but at times, and always from statistical or microscopic thermodynamics point of view. We are yet to discuss about that area, fundamentals of which will be discussed in week 6 lectures, which is going to come up shortly for this course. This equation that we have, it represents the general principle of law of mass action, which deals with mass conservation concept, which always has to be satisfied during a chemical reaction. Since we are not dealing with any nuclear reactions, mass always remains conserved. So, if we are keeping track of, for example, nuclei of different chemical elements, then their numbers are going to remain conserved all through the chemical reactions, and the above equation definitely plays a role in conserving that. Thereby, it gets the tag of law of mass action. The above equation can help calculate the equilibrium composition of a chemically reacting gas mixture, and that is what we will be definitely interested in. That is, when we look at a chemically reacting gas mixture comprising of different reactants and product species, and probably also intermediate species which are involved in course of the chemical reactions, then what will be the equilibrium composition of the mixture is a big question to be answered, and this equation will go a long way in helping us answer that query. In order to answer that, we will take up an example. So, we will look at combustion of hydrogen, molecular hydrogen, which we consider as a fuel, and molecular oxygen, which is considered as an oxidizer, and let us say they are getting combusted in a cryogenic rocket engine. We will try to model the chemical reactions which may be involved in the process. Let us assume in the beginning that the fuel oxidizer ratio has been defined. So, that is specified independently, and based on whether it is a fuel lean mixture or a fuel rich mixture or a stoichiometric one, we would be able to get what is basically the fuel to oxidizer ratio. Let us say in terms of mass. The fuel and oxidizer would react through different chemical reactions, and the relevant chemical equations have to be considered. There may be numerous intermediate species formed which need to be accounted, and this is not a very easy job to do, and there is no unique approach associated with this. We have to find ways of rationally implementing this. It is assumed that through all these chemical reactions, the products of combustion are finally formed when an equilibrium chemically reacting gas mixture exists at a certain pressure and temperature. The pressure and temperature cannot be calculated using this above procedure. So, they have to be known a priori from either measurements or defined as per prior experience or obtained through some independent estimate, let us say a numerical simulation or something, but that has to be stated independently, because this cannot be defined or calculated based on the procedure that we are going to discuss. The species that we are going to consider are based on prior knowledge or some educated guess. Of course, experience does help, and prior familiarity with the chemical reactions would definitely help. And based on that prior experience or knowledge, one may go ahead with definition of these following species concerning combustion of molecular hydrogen and oxygen. We include atomic species of both. We include the OH group as well as H2O, which will be formed as a dominating combustion product. And 4 chemical reactions are considered on an ad hoc basis, where we talk about dissociation of molecular hydrogen and oxygen, molecular hydrogen reacting with atomic oxygen to give the OH group plus H, the atomic H, again OH and H reacting to form H2O. So, these are 4 out of many possible chemical reactions that one may imagine, but it is important for us to ensure that we are accounting for all the species which are actually going to be associated in such a chemical reaction. Now, if you look at this particular equation and we are talking about the equilibrium constant Kp1, let us say 1 for the first equation, then we remember going by the equation that we had derived earlier over here, that we have to have a product of the partial pressures of the reactants and products raised to appropriate values of nu I, and remember that for the reactants we will have negative values of nu i's. Keeping that in mind, you see that on the reactant side we have a negative index, while product side we have a positive, and those positive or negative indices have to do with the stoichiometric mole numbers, and thereby you get an expression for Kp1 pH by under root pH2. Similarly, if you go to the second equation, you have an expression for Kp2. Again, notice the indices, that is very, very important. When it comes to this equation, all the mole numbers are 1, but for the reactants they are negative, for the products they are positive. The same holds for the fourth equation, reactants negative and products positive. Thereby, you end up getting 4 equations, and as long as you are able to figure out the values of the Kp's varying from 1 to 4 from some charts or tables, you should be able to frame 4 algebraic equations, independent algebraic equations, to solve for those unknown partial pressures. But you would soon see that the number of unknown partial pressures are going to be more than the number of equations, because you have considered 6 species anyway over here, and therefore, we are falling short by 2 equations. One way of looking at it could be that we add 2 more chemical reaction equations, but that is not the rational way ahead. We do not incorporate any more chemical reactions, rather we include 2 very important constraints, and they need to be necessarily fulfilled. Therefore, we prevent ourselves from going ahead with any more chemical equations, but rather try implementing the Dalton's law of partial pressure, which states that the total pressure which has been independently prescribed must be a summation of all the partial pressures coming from the 6 species, and the fuel oxidizer ratio that has been defined right in the beginning, that gets translated exactly into numbers of nuclei of the reacting hydrogen and oxygen atoms. So, we define them as NO and NH respectively, and we emphasize on tracking the number of oxygen and hydrogen nuclei which are participating in the chemical reactions. Since no nuclear reactions are involved in this, the NH and NO which are defined in the beginning in terms of fuel oxidizer ratio, they would remain invariant. That is a very, very important principle, and therefore, all through the NH by NO ratio needs to be conserved, and we definitely need to work them out. So, NH and NO have to be obtained depending on all the reactants and products that we are involved with in the system of chemical reactions that we are considering. These numbers, they represent what? They represent the number of nuclei per unit mass of the gas mixture. As I said that when we define the fuel to oxygen ratio, then we are most often going to deal with them in terms of mass, and therefore, these numbers are also defined in terms of mass, per unit mass of the gas mixture. We introduce the mole mass ratio eta in the calculations for convenience. We defined that eta I was defined in a manner like this, where Ni, the scripted N, is number of moles of species I, and capital M is the total mass of the mixture. That means that ratio gives you the number of moles of species I per unit mass of the mixture. Now, in order to plug that in over here, you have to bring in the Avogadro's number, which is the number of particles per mole, and then that product of eta and Na will ultimately give you contributions of the number of nuclei coming from different species per unit mass of the gas mixture. Now, 2 hydrogen nuclei will be contributed by each H2 molecule, 2 hydrogen nuclei from one H2O molecule, while 1 each from H and OH groups. Therefore, the respective weightages here, you have a 1 here and a 1 here respectively. That ultimately will give you the number of nuclei of hydrogen participating in the chemical reactions. In a very similar manner, you can work out the number of oxygen nuclei which are participating, again keeping track that the oxygen molecule contributes 2 oxygen nuclei, while atomic oxygen, water and the OH groups, they contribute 1 oxygen nucleus each. Thereby, when it comes to the NH by NO ratio, you get a form like this, and obviously the Avogadro's number occurs both in the numerator and denominator will thereby get cancelled. Additionally, we would like to bring in the partial pressures here in the equation. They are still in terms of eta, for which we have to invoke the equation of state of perfect gas applied to each one of the constituent species in the mixture. So, it is P I times V is equal to eta I times RT, R being the universal gas constant, which gives you an expression for eta I in terms of P I, and the remaining portion of course will be a common factor for all, which will ultimately cancel out. Thereby, you will end up getting the ratio of the number of nuclei of hydrogen and oxygen coming out to be this in terms of this equation, where all the partial pressures of the 6 species are involved. Now, if you recall, we have 6 equations in all concerning the 6 partial pressures, and in principle they can be solved in order to obtain each one of the partial pressures. Now, the Kpt values, the equilibrium constants, where are we going to obtain them? They can be obtained from tables, the Janov thermodynamic tables, which were made available through a publication by Stahl in 1971, which is still being widely used, and it can also be derived directly from statistical thermodynamics, which is a little more involved. the chemical equations must be independent. So, what does that mean? We cannot obtain one chemical equation by adding or subtracting the others. So, that is how we can ensure that all the chemical reactions that we are including, the equations that we are including are independent to each other. What does that ensure? It ensures that the system of algebraic equations that we are obtaining, they are independent in nature. The choice of chemical equations, apart from this independent constraint that we have imposed over here in point number 3, is rather arbitrary, but that does not mean that we go about doing it in a very blind manner. The important point is that all the relevant species that might be present as either intermediate species, reactants, products, they have to be included. Thereby, prior knowledge and good educated guess does work. If that is not adequately available for a given situation, then the safest approach to go about it is include all species that are made up of all possible combinations of the various elements that are present. This is a foolproof process, though it is a little more cumbersome. In the process, you may end up getting a larger number of equations, but then there are going to be larger number of partial pressures also to be solved. If some of these assumed species are actually negligible, the partial pressures will come out to be very small when you solve the equations, which is not known a priori of course, but they will ultimately come out to be very small, and that basically means that these are trace species. That means they are going to have a very minuscule contribution in the overall reactions. So, that is as far as the chemical composition of an equilibrium gas mixture calculation is concerned, and we went through that example in order to get a better grip over the idea. We will finish this lecture by going to the last point that we have in this week, heat of reaction, for which we consider a certain equation here where molecular hydrogen reacts with a half a molecule of oxygen to give the OH and H groups, and let the reactants be at a temperature T ref to begin with, and at this temperature let their sum total enthalpy be calculated and obtained, and of course weighted by their respective stoichiometric mole numbers. So, we are stressing on this reference temperature and calculating the enthalpy of the species at that reference temperature to begin with. This is a very important point to be noted. Let the chemical reaction take place at constant pressure. This is another very important constraint that is being imposed, which has a big connection with the concept of heat of reaction. And after the chemical reaction takes place, the products are formed. We have to finally either extract or add enough heat from or to the system, so that the products are again brought back to the T ref temperature. So, we begin everything from T ref, the reaction takes place. If it is an exothermic reaction, then obviously the temperature of the products will go above T ref, maybe much above T ref. If it is an endothermic one, it will go below T ref, but you either extract or add enough heat so that it gets restored to T ref temperature. So, we are talking about restoring the products to T ref temperature. Now, the total enthalpy of the products at T ref can also be calculated. Now, the heat that was either extracted or added from the thermodynamic system or to it is called the heat of reaction. Now, this heat extraction or addition was done with the intention that the products are maintained at T ref. That needs to be kept in mind. And where did this heat go? So, if we invoke the first law equation and we try to specialize it for a constant pressure process, which we are imposing as a constraint, then obviously that heat transfer, whether it is an addition or a subtraction, will go in to change only the enthalpy. Enthalpy of what? The mixture. Essentially the mixture of the products once the chemical reactions have taken place. Hence, the heat transfer is equal to the change in enthalpy of the products. Now, heat of reaction at the reference temperature T ref is indicated by this expression delta H R, R for reaction, and we mention the reference temperature on top. So, what do we get finally? We get that delta H R T ref must be equal to the enthalpy of the products at T ref minus the enthalpy of the reactants at T ref. And how do we calculate it? It must be the summation of the enthalpies of the products minus the summation of enthalpies of the reactants at the same temperature T ref. And expressed in terms of a summation, it can be indicated like this, where again nu I indicates the stoichiometric mole numbers of the reactants and products with negative values for reactants and positive values for products, and the subscript A I basically stands for the different species which are involved both from the reactants and product side. Now, delta H R at different T ref values for a given chemical reaction can be calculated using the Janaf tables and also by using statistical thermodynamics, and is a very important concept in itself when we are dealing with chemically reacting gas mixtures. So, with this we came to the end of the week 5 lectures. In this lecture we discussed about equilibrium chemically reacting gas mixture. We discussed about Gibbs free energy and chemical equilibrium, and we defined the equilibrium constant. We derived an expression for it in terms of the partial pressures of the different species of reactants and products in the mixture. The process for obtaining the composition of an equilibrium chemically reacting gas mixture was explained through a suitable example, and the concept of heat of reaction was discussed. Thank you.